So here we're going to talk about Taylor series, which is another application of the power series. So remember how I talked about how we could download different apps for our cell phone, or you could download different power series apps, so to speak. So one of those apps that we downloaded was the Maclaurin series, and the Maclaurin series required taking an infinite number of derivatives, or a whole bunch of derivatives, and evaluating all those derivatives at zero. The Taylor series is a very, very similar concept, but it's more general. It's like a multi-tool for multi-tools, if you will. And so instead of finding all those derivatives and evaluating at zero, here we can evaluate at 1, 2, 3, 4, any number, we'll call it A, where the derivatives are all defined. So this is the Taylor series. If you just think about it as an extension of the Maclaurin series, it won't be that big a deal at all. I think you're in for a little treat here. Power series. So Taylor series and approximations. So we've learned about power series, and we've done this in 2 steps. We learned to find the power series. We did this mostly using geometric series or Maclaurin series, and then whatever algebraic manipulations we could do to those. And then we found where those series were convergent. The second point and the interval of convergence provides us a clue toward our next step. Example 1. Review 2 power series for 5 over 4 plus x. You may recall that 5 over 4 plus x was one of the examples we looked at in a previous example. And we found earlier, or we at least claimed earlier, that this was equal to the sum from n equals 0 to infinity of 5 times negative 1 to the n times 3 plus x quantity to the n. Earlier, we found that the interval of convergence for this was negative 4 less than x less than negative 2. And you'll notice that halfway in between this negative 4 and negative 2, the exact midpoint, would be where x equals negative 3. And in particular, notice that if you take that negative 3 and you substituted it in to the power series, you get a 3 plus negative 3, and 3 plus negative 3 is 0. So it's kind of an indication of where the center of this first series is. We also have that same series, 5 over 4 plus x, could be written as using another version of the geometric series as the sum from n equals 0 to infinity of 5 over 4 times the quantity negative x over 4 raised to the nth power. We didn't go over this one earlier, but you should be able to see that you could factor a 4 out of the denominator. That gives you that 5 over 4. And then you could rewrite the plus x, which is now a plus x over 4, as a minus x over 4. And hence, that's where the negative x over 4 comes from. Here, we've done enough questions like this to notice that our interval of convergence will be from negative 4 to positive 4. And the center of that region between negative 4 and 4, the center of that would be at x equals 0. Notice again that if we took that x equals 0, we substituted it into the power series that we found, it will give us a 0 over 4, or like a 0 to the nth power. It's kind of the same type of thing. So before we move along, notice that this means that there are multiple power series. Each power series comes with its own interval of convergence. Generally speaking, a bigger interval is better. And each interval has its own center. Okay. So the power series representation for a function is not necessarily unique. Notice that one function may have more than one power series representation. These series have different intervals of convergence. And of particular note, the center of the intervals of convergence is different, right? Both at 0 and negative 3. And so this is our first hint of this idea of a center of an interval of convergence, which is going to be a big thing in our next topic, the Taylor series. Back to power series and the center of the power series. So this idea of the center of a series is not new to us. This isn't the first time we've generated a power series with a known center point. In particular, the Maclaurin series formula, f of x equals to the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 times n factorial, or over n factorial, times x to the n, generates a series centered at x equals 0. To see this, notice here's the x equals 0, there's the 0, and also note that if we were to take this x equals 0 and substitute it into the power series, each of the terms would include a 0 to the nth power. This formula and the accompanying derivation that we already went through can be modified to generate series centered at x equals a, so a shifted series. So definition, if f has a power series representation or power series expansion at x equals a, that is, if f of x equals the sum from n equals 0 to infinity of Cn times x minus a quantity to the nth power, when the absolute value of a minus x minus a is less than r, then its coefficients are given by the formula Cn equals the nth derivative evaluated at a divided by n factorial. We call the series above a Taylor series. So that definition is a little bit wordy. It's a little hard to see what's going on. But what I'd like to do is point out the difference between the Maclaurin series, where we're evaluating the function at 0, and the Taylor series, where we're evaluating the derivatives at a, as well as the Maclaurin series, where we have an x. Notice x to the n is the same as 0 to the n when x equals 0, centered at 0, versus the Taylor series, which has an x minus a to the n. Notice when x equals a, center of that series, this would evaluate to 0. So it'd be a minus a raised to the n, or 0 to the n. So in truth, this Maclaurin series is actually a special case. Special case of the Maclaurin series, or of the Taylor series. When a equals 0. Example 7.1. Find the Taylor series for f of x equals 1 over the square root of x centered at a equals, and we're actually going to do this at a equals 16. So to do this, we need to make the table of derivatives. And so we're going to look at f of x and f prime of x and f double prime of x and f triple prime of x and the fourth derivative. Okay, and we need to find each of these. So remember that when you are working with roots and fractions, it's easiest to write this as a fractional exponent. So we'll write this as x to the negative 1/2, which tells us that our first derivative is going to be minus 1/2 x, the minus 3/2. The second derivative will be positive. And then let's see if we can keep our pattern here. So we're going to have 1 times 3 over 2 squared x to the negative 5/2. And then it's going to be negative 1 times 3 times 5 over 2 cubed x to the negative 7/2, positive 1 times 3 times 5 times 7 over 2 to the 4th x to the negative 9/2. So we can clearly see the pattern of what's going on in our terms. So now we need to evaluate each of these at, oh, so I'm cutting through my 2's. Let's try that again. And the next one's going to be at, come on. There. We want to evaluate at x equals 16. Okay. So the first term is going to be 1/4. The second term is going to be, looks like -1/2 times 1/4 cubed. Next term is going to be positive, so it went positive, negative, positive. So we're going to get 1 times 3 over 2 squared times 1/4 to the 5th power. Remember that the square root of 16 is the 4. That's where all these 4s are coming from. And then you got the 1/2 power be 4 to the 1. The 3/2 power would be square root of 16 is 4 cubed. There's the 4 cubed. Next one's going to be negative 1 times 3 times 5 over 2 cubed times 2 cubed, not 3 cubed. My bad. 2 cubed times 4 to the 7th. Then positive 1 times 3 times 5 times 7 over 2 to the 4th times 4. Oh, sorry, 1/4 to the 9th. This last one should have been 1/. Now let me change my color. Should be 1/4 to the 7th. Okay. And notice that 4 would be up here, or 4 would be 2 squared. 4 cubed would be 2 to the 6th. 4 to the 5th would be 2 to the 10th. 4 to the 7th would be 2 to the 14th. 4 to the 9th would be 2 to the 18th. Each time we're doubling the power. So we could write this stuff a little bit more concisely as like 1/2 squared minus 1/2 to the, so it's going to be 2 to the 6th plus 1, so this is going to be 2 to the 7th plus 1 times 3 over 2 to the 12th. We're adding 5 to our power each time. 1 times 3 times 5 over 2 to the 14 plus 3 would be 17. And that one should have been negative. And then positive 1 times 3 times 5 times 7 over 2 to the 18 plus 4, or 22. Okay. So this gave us all of our the root part of our, kind of like the derivative part of our coefficients. We got to put this stuff together in order to find our full coefficients. And let's see if we can do that below. So what we're saying is that the 1 over the square root of x is equal to, and here we'll have 1/4, or 1/2 squared. And that's this term here. Okay. Then we will subtract out 1/2 to the 7th divided by 1 factorial times x minus 16, all raised to the 1st power. So this right here is the 1 over 2 to the 7th negative. That's that part of the coefficient. And then we have the 1 factorial from the Taylor series formula. We have the x minus 16 from the Taylor series formula. And we keep going. And so we'll add 1 times 3 over 2 to the 12th, all divided by 2 factorial. I'm not going to simplify because I want to make sure that the pattern is obvious. This will be times x minus 16 squared. So here, there's the 1 times 3 over 2 to the 12th. 1 times 3 times 2 to the 12th, and it's plus. Okay. And then the 2 factorial comes from the Taylor series formula. The x minus 16 comes from the Taylor series formula. Keep going. So then minus 1 times 3 times 5 over 2 to the 17th divided by 3 factorial times x minus 16 to the 3rd power. So this would be from the derivative that we found. The 1 times 3 times 5 over 2 to the 17th is from the derivative we found. The 3 factorial and the x minus 16 to the 3rd, those are from the Taylor series formula. You can do a couple more here. So then we go plus 1 times 3 times 5 times 7 over 2 to the 22nd over 4 factorial times x minus 16 to the 4th. Here, the 1 times 3 times 5 times 7 over 2 to the 22nd. That's this part of the coefficient. The 4 factorial that's also part of the coefficient comes from the Taylor series formula. And then the x minus 16 to the 4th is from the Taylor series formula. At the end of all this, it's very important that we want to say we're going to continue on in the same manner. It's very important to have a plus dot 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 because it says continue on in the same manner. You might ask, why is it that we would say plus instead of minus? Well, it would be okay to say minus. If I said plus here, I'm assuming, because I know that the terms alternate sign, that I would be assuming that the next term out would be a negative term, following term out would be positive. And so I'm assuming that the sign is going with the term, not with that particular plus. So it works either way. But there you have, where did it go? Sorry, I lost it. There you go. There you have the Taylor series for f of x equals 1 over square root of x centered at a equals 16. Example 3. Find the Taylor series for g of x equal to x minus x cubed centered at a equals 2. So this question is going to begin like the last one. So we have g of x equals x minus x cubed. G prime of x will equal 1 minus 3x squared. G double prime will equal negative 6x. The third derivative will equal negative 6. And the fourth derivative will equal 0, as will all the ones after it. Okay, we can evaluate these when are at a equals 2. So a equals 2. So g of 2 would be 2 minus 8, negative 6. G prime would be 1 minus 12, minus 11. G double prime, negative 6 times 2, negative 12. G triple prime, negative 6. And then 0 from that point forward. So if we put all this stuff together into a Taylor series, what we're saying is that g of x, which is x minus x cubed, is also equal to -6 plus minus 11 times x minus 2 all over 1 factorial minus 12 times x minus 2 squared over 2 factorial minus 6 over 3 factorial times x minus 2 cubed plus 0. All the other coefficients will be 0. So here we have a second representation, a second Taylor series for g of x. Notice again that your denominators are going to be divided by 0 factorial, 1 factorial, 2 factorial, 3 factorial, and you have those, the x minus 2's from the formula that are sitting in with each of the terms. X minus 2 to the 0, x minus 2 to the 1, x minus 2 to the 2, x minus 2 to the 3, plus 0, 0, 0, etc., etc., etc. So there we found a Taylor series for g of x equal to x minus x cubed, but this time centered at x equals 2 instead of centered at 0 like the original function that we're given. So the last time I taught this, I noticed something interesting. I noticed that sometimes students struggle with the fractional exponents and the negative exponents associated with radicals and fractions. So I just want to encourage you to do a quick review on your own of how fractional exponents work, how negative exponents work. Maybe take a look again at example 7.1 and see whether that can work for you. But overall, I hope you saw that the Taylor series is just like what we did with Maclaurin series, pretty straightforward. It's a fair amount of writing, but it's not actually that difficult. You just kind of got to remember where you are at in the process.